another statistical lecture. Of course, before I get started today, I want to say I've already published the last recording on YouTube, so I'm also recording this as well. So today's topic is actually going to be normal approximation to binomial, of course, in the outline. I'm going to have a review on central limit theorem. Then I'm going to walk you through the proof of normal approximation to binomial. Then we're going to also talk about application. Please, I need everyone to stay focused because what we're going to be doing now is very, very crucial. And the moment you get stuck or you need clarification, I need you to direct that to me. I'm going to start with the, review central limit theorem again, because what we want to do today, it has a connection to central limit theorem. And that is the reason why I'm going to start my review from there. You already know that what central limit theorems talk about. If I have random variables y1 up to yn, okay, that I choose randomly from a population, whose the distribution is not normal. And if we go into such population several times and, provided the sample size is large, we expect the distribution of the statistic to converge to approximately, converges to normal distribution. Okay, that is what the central limit theorem talk about. The statistic may be sum of random variable. The statistic may actually be sample mean, and the statistic may be proportion as well. And that is what I'm demonstrating right now. And we believe that in the end, whatever statistic of interest, like right here, the statistic of interest is UN. Okay, so if I make an attempt to actually obtain the CDF of that particular statistic, when n tends to infinity, and that we converge to the CDF of a normal, of a standard normal distribution. I needed to take note of that. The statistic we actually want to figure out depend on the parameter of interest. I told you from day one, the interest is on estimating unknown population characteristic value that I call parameter. Okay. I want to go into, we could have a situation where the parameter of interest may not be sample mean, may not be, it may be proportion. Okay. And of course, anything that has to do with proportion, before you talk about proportion, of course, we are actually interested in a certain characteristics in the population. Okay. And I told you the other time, it could be the proportions of Americans who approve the job the president is doing, or the proportion of Minnesota with a particular disease, or the proportion of a particular country that have more than certain threshold, with regard to our household income. Now, let us suppose that Y as a binomial distribution. Binomial distribution is a probability distribution, that actually, characterize by dichotomous outcome. Okay, there are two possible outcomes. That's what I mean. Now, with n trials, the difference between binomial distribution and Bernoulli distribution is just the numbers of trials involved. Whether Bernoulli or binomial, the two of them is characterized by two possible outcomes. We got one numbers of trial in Bernoulli and more than one trial in binomial. And of course, we have certain characteristics in mind that we're actually going to call success. And that is why I said the probability of success on any one trial denoted by P. And what if in the situation if we want to find the probability of Y less or equal to B? Of course, if we want to do that, we're going to use binomial. Now, the origin of binomial can actually be traced to Bernoulli. Okay, I want you to see the connection. Please follow my lecture with analytical mind and with a practical mind. I need you to pay attention to notations, symbols. I want to talk about the origin of binomial now. Binomial is a generalization of Bernoulli. If I have a random variable x that follow Bernoulli distribution, where I have, x1, x2, and the like, and if I have more than one trial, okay, and I sum the Bernoulli random variable together, then I'm actually going to have binomial. Don't forget, every Bernoulli trial, the probability of success is P, is the same. So if I consider sum of Bernoulli now, if you take a look at what I circled, the sum of Bernoulli to n, which means I'm going to have n numbers of trial, we're no longer working on Bernoulli, but binomial. The sum of Bernoulli is binomial. Okay. And of course, xi, because we got two possible nature. Okay, for each trial, we're actually going to introduce a label. Okay, the success one is going to be 1, and the one we don't want is going to be 0. If I'm interested in the proportion of Americans who approve the job the president is doing, if I have selected a random sample of Americans, maybe I have 1,000 Americans. If I go from number 1 to number 1,000, the same question is what I'm going to ask from them. What is the question? Do you approve the job the president is doing? It's either it tell me yes or no. Yes is 1. No is 0. What am I interested in? I'm interested in the totality of the numbers of Americans that will say yes. And that was the reason why I'm summing. Why call the sum of x? Because it's going to be like 1, 0, 1, 0, 1, 0. Okay. When I do that, for each Bernoulli, the mean is expected value of x is p. And the variance of x is p into 1 minus p. This is from statistical theory. What of in a situation where I now want to consider large sample, and I'm interested in the sample fraction of success, the sample fraction of successes, then I actually need to get average. Don't forget, my y is summation x. So y divided by n is the same thing as summation x divided by n, which is going to be x bar. Okay? Which is going to be x bar. And you know what? Now that I know the expected value of x, and I know the variance of x, can I deduce the expected value of X bar and the variance of X bar, yes, we can actually deduce that. And of course, the expected value of X bar is going to be the same thing as expected value of X. But the variance of X is different from the variance of X bar. Okay, and that was what led us to having this right now. Okay, now let me tell you this. Excuse me. Why do we need normal approximation to binomial? Why do we need to go from a skewed distribution to normal distribution? Then it means the reason why we want to go from skewed distribution to normal distribution, because we got a lot of benefits using normal. I'm going to say that again. In statistical framework, we normally want situation where the underlying distribution of the population is going to follow normal, even though right now they don't follow normal. And why are we interested in applying central limit theorem so that the statistic computed from that is going to follow normal? Is because we got a lot of benefits using normal distribution. I'll first tell you those benefits right now before I move forward. Number one, when you look at the shape of a normal distribution, of course, the normal distribution has a double bear shape, right? It is symmetric. That very shape is fantastic. That very shape describes some, natural phenomenon. That very shape actually represents some processes. When you take a look at that shape depicts some reality. I'm going to give you an example now. We're talking about blood pressure. A large number of patients in a very large population, large number of people in a very large population, we have high blood pressure. Oh, sorry, let me say that again. A few numbers of people in a large population, we have high blood pressure, and just few, we have low blood pressure. But the majority of the population, we have a value of the blood pressure that is close to the average. I'm going to say that again. Few, we have high blood pressure in a large population. Few, we have low blood pressure from a large population, but the majority of them, we have a blood pressure, the value that is close to the average. And that's a typical shape of a normal distribution. I'm going to tell you some other reason why normal distribution is very, very important in statistical analysis. The normal distribution is very easy to compute, very easy to use. When you have a distribution of population in other form other than normal, we normally experience mathematical complexity. We always want to run away from that. We don't want to waste our time. Problem in reality will not wait. It's timely. We need to address the problem on time. Otherwise, we're going to get consumed by it. And that is the reason why we need to have a kind of model, very simple model. That's one of the benefits. Another benefit of normal distribution is because it has a linkage with central limit theorem. Normal distribution has a link to central limit theorem. Because when central limit theorem applies, irrespective of the probability distribution of where you are choosing your data from, provided you have a sufficient large sample, the distribution will convert to normality. And let me also tell you this. Many statistical tests rely on assumption of normality, like a t-test, analysis of variance test, name it. even absorption of the error time in regression analysis and so on like that, they rely on the absorption of normality. So there's no benefits from normal. Before I go into the condition of approximation, I will also say this. So people may want to argue this with me. Why do I need to worry myself about taking last sample? I can standardize. If I have data set, if you follow exponential distribution, if I know the mean of the data, I know the standard deviation, I can compute a standard random variable. And with that, it will follow normal distribution. No way. Standardization does not change the shape of the data. I'm going to say that again. When you standardize your data set, the essence of standardization is to scale to the feature, because you could have some value that could be very high, some values could be very low. Standardization does not change the shape of the data set. Does that make sense? So if you have exponential data and you standardize, the shape of the standard variable will still be exponential. But the only thing that will change is just the mean is still going to be 0 and 1, but the shape does not change. Does that make sense? Okay, now I've justified why we need to go from, a skew distribution to normal. I've just narrated the benefits we can derive from normal distribution. Another benefit is table. We have table in existence that we can use, statistical table. And of course, I've told you the other time why we need to standardize even normal, okay? Because for us to prevent having an infinite numbers of area table. Does that make sense? Okay, and let me also briefly tell you about the origin of normal distribution. 1733. The first person that discovered normal distribution was actually De Moivre's. 1733. You know what De Moivre worked on? De Moivre worked on the title that I'm presenting today, that we call normal approximation to binomial. That occurred in 1733. You know, the origin of the normal can be traced to three different scenarios, three different mathematicians. I just mentioned De Moivre in 1733. There's another one, Laplace in 1783. When Laplace was working on measurement error, okay, he discovered normal distribution as well. Then the last one was in 1809 by Gauss. Gauss was working on the analysis of astronomical data. And that is why at times normal distribution can also call Gaussian distribution. Okay, now having justified that, I want to go into the condition for approximation. If I'm working with binomial, why do I need normal approximation? Because when the sample size is large, okay, using the conventional binomial probability mass function would be very tedious in terms of computation. I'm going to say that again. When the sample size is large, if you want to figure out the probability of a random variable with a binomial, okay, it is going to be so complicated. And that's why we need a way out. Okay, and that is the reason why we need approximation to normal. We also have binomial approximation to Poisson, but the one I'm interested in today is binomial approximation to normal. Now, if I'm seeking that, we got a condition. Provided this guy, if you take a look at that guy, is the what I circle, that is like within the 3 standard deviation, right? That we can tolerate. What you see there is I'm going to show you this, and I'm going to write this now. Give me 1 second. This, what you have inside the square roots, is the variance. And the square root of that is the standard deviation. Take a look at that. Now, this guy must be within 0, 1. Why is it that it has to be within 0, 1? Because proportion is within 0, 1. Provided we can have that, so which means within, below the mean, we actually be greater than 0, and above the mean, we have to be less than 1. Okay, we got a rule here. Now, I'm now going to go into the theorem now. The normal approximation to binomial. Okay, so if xn is a binomial variable with parameter n and p, right? Then don't forget, in binomial, this is going to be the mean for binomial. If the mean for Bernoulli is p, the mean for binomial is np. Okay, don't forget, binomial variable is the sum of Bernoulli. So summing p in n time, it's going to be np. And the variance for binomial is going to be np 1 minus p. The variance of Bernoulli is p into 1 minus p. Okay, and of course, our central limit theorem we apply as n tends to infinity. Okay, we expect that to follow a standard normal distribution. Take a look at that. Any question? Okay. Now, I want to walk you through this now. Theoretical way. Okay. Binomial probability function can lead to normal density function. Because what we're trying to say now, we're trying to say that xn is a distribution, as in x follow normal now with np, the mean. That will be the mean of binomial and the variance. You are now assuming the mean of Bernoulli, the mean of binomial to now be the mean of normal. You are also assuming the standard deviation of binomial to be that of the normal, but provided n is large. If I want to plug this into normal density, this is what I have, right? You remember in the normal density, okay, in the normal density, this guy here, in the normal density, is what? Sigma squared, right? Right? This guy here, NP, is going to be what? Mu, right? If you know the normal density, okay? And this guy here, that is the sigma squared. Take a look at that. Okay? Now, you know what we want to do now? Can we have a way to start from the first principle? We want to start from binomial probability mass function. We're going to tens n to infinity. Can we derive normal density from that? That's what I want to show you now. Let's start the proof. If I want to start a proof, we're going to make use of the Stirling formula. The approximation of n factorial. You've heard about factorial, right? Approximation of n factorial is the square root of 2 pi m exponential raised to power minus m raised to power n. Okay? Everyone understand that? And I want to start from binomial now. This is binomial, right? You see that? That is the probability density probability mass function of a binomial distribution. Now, what do I want to do now? I want to use the idea of the Stirling formula, n factorial equal to that, okay? And k factorial now, give me 1 second. You're going to see something now. Okay, using Stirling, k factorial is this guy. Okay, n minus k factorial, okay, is this guy. Any question? We're using Stirling formula. Any question? We just substitute for factorial using Stanley formula. Okay. Now, the next thing we're going to do now is to use the most important in mathematics, algebra. We need to simplify. When you take a look at this, I can just bring out this by way of factorizing. Take a look at all of that. Okay, if you simplify, that's what you're going to have. Then from there, I can rewrite that as that. I can rewrite that as this. Take a look at that. Okay. Now, if you take a look at this guy here, right? And this guy here, okay? We want to go into Taylor series or Maclaurin series, okay? Let's say, for instance, the ln of x. If we call this x or that x, okay? If I let me show you that identity. You know, if you take a look at, for instance, four of us take a look at this, okay? This can be expressed as this. That's from mathematics. When I have ln of that, it's also, you know why? Try to simplify 1 plus k minus p divided by m minus. If you simplify that, you're going to go back to mp over k. The idea is I'm just bringing out 1 so that I will be able to use mathematical rule of ln into 1 plus x. The same thing also applicable to this guy. Take a look at that. After that, now that I now have it in ln into 1 plus, then I can now impose this. This is coming from mathematical rule. Ln into 1 plus y equal to that. You know what our y is going to be? Our y, okay, y is going to be this here, and y is going to be this guy here. Does that make sense? Okay, so y is going to be that, and by the time I plug that in, okay, by the time I plug that in, for your information, initially there's no ln. I introduce ln. Okay, there's a way I can eliminate that ln. I'm still coming back. When when I have x, for instance, let's say I have x, right? And I introduce ln. I got ln of x, right? If I want to eliminate ln, I'm just going to do exponentiation. That's mathematics. I introduce ln, right? And I want to get rid of the ln, then it's going to be exponential raised to power ln of something. Now, I need you to take a look at what I have now. I introduce ln. Okay. So, if you take a look at what I have here, okay, the ln of this guy now, where is that coming from? That is coming from here. For now, I'm going to leave the last part. For now, I will leave the last part. I'm focusing on that one. I introduce ln. Okay. Now, take a look at this now. When I do that here mathematically, ln is log of natural, right? Log of a, b would be log of a plus log of b, right? Take a look at it. That's why you have this. Okay, it's going to come down plus that. Does that make sense? Now, when you have this now, we now want to go back applying ln of this and the ln of this. Putting into consideration, don't forget the ln into mp divided by k. We've already said it's going to be written as this, right? And the ln into n into 1 minus p divided by that is going to be written like this, so that applying this guy now, applying this guy now, okay, that is what is going to lead us to this. That's what's going to lead us to that. When we simplify, finally, we're going to get this guy. Okay? How do we how do we remove the ln? Right? We exponentiate. Do you see exponential now? We put exponential on that. So because if I want to, there was a ln here, right? I want to remove the ln, right? Then it's going to be exponential of that. That was what I said the other time. Now, if I have the exponential, which means the result that I have now is this guy, right? Okay. Now, next thing is I've already gotten that for the whole of this one. I simplify that to exponential raised to the power something. Now I want to work on this. It is time to work on this now. I want to work on that guy now. That guy, the former one, is now exponential raised to the power negative something. Now I now need information. Take a look at this. K minus NP, the deviation, okay, can be, we expect it to be in the order of square root of n, according to the movers. Okay, if that should be the case, it's actually suggesting K minus NP is approximately square root of n. Now, if K minus NP is approximately this, then what is n minus K? Okay, if I want to have n minus K, what is K from here? K here will be equal to what? K here will be equal to square root of n, right? Plus what? Plus NP, right? Plus NP. Okay? If this is K from here, that implies K equal to that. If I know K, then what is n minus K then? Of course, it's going to be n minus, in parentheses, square root of n plus NP. Okay? If you take a look at what we have now, so this is approximately this guy. Then if I know K and I know n minus K, then I can find K times n minus K, which is going to be this. Now, what is the takeaway from here? The takeaway from here is I want to substitute for this, K into n minus K. So K into n minus K is this guy. Okay? By the time this guy comes in, I'm going to have 2 pi. Okay? And, there is n squared p into 1 minus p. Okay? And you can see here, by the time you plug that in, okay, because you actually, it is this guy that you plug in, then you're going to have this. Now, the moment you have this here is more or less like 1 divided by square root of 2 pi sigma squared. What is sigma squared now? The sigma square is NP into 1 minus P. That theoretically we can derive, normal density from probability mass function of binomial. Okay, now that is a theoretical development. But let me tell you this. If I want to approximate, if I can withstand the rigor of mathematical complexity, using binomial for binomial situation will give us the correct results, the actual results. But when you use normal approximation, there's going to be error. You can't get the exact result because you're only going to get approximate value. Now, How are we going to improve? How can we minimize the error due to approximation? Sorry. How can we minimize the error due to approximation? We need continuity correction. Don't forget, we want to go from discrete random variable to continuous random variable. We're actually approximating binomial probability distribution, okay, with normal density function. There's going to be an error. How can we minimize the error? Because of that, we need continuity correction. If I want to find the probability of S equal to n using the normal density, then I need to subtract and add 0.5. If I want to find the probability of S greater than n, I'm going to add 0.5. S less or equal to n, I'm going to, it's going to be adding 0.5, and that will be less than. So this, depending on whatever you want to do, depending on what you want to do, this is a continuity correction. Okay? Now, I'm going to go into an example now. Candidate A believes that she can win a city election if she can earn at least 55% of the vote in precinct 1. Precinct 1 is like a district, like within the city. Okay? She also believed that about 50% of the city voters favor her. About 50% of the city favor. That's a population parameter. It means the population parameter is 0.5. If n equal to 100 voters show up to vote at precinct 1, what is the probability that the candidate will receive at least 55%? At least 55. That will be, if you come back to this here now, at least 55, you're actually going to come here. Greater or equal. Don't forget. Now, if you take a look at this now, this is the data. This is what you want to find. The probability of y over n greater or equal to that. Don't forget, the mean is going to be 0.5. And y over n, don't forget, is the x bar. Okay, and don't forget, so if I want to interpret that, okay, I'm actually, this is what you're going to see. Y over n, okay, minus 0.5 divided by that. But right here, you can see I have 0.55. I did not apply continuity correction here. Okay. And there are some questions like that I mean, not necessarily, provided I have, if certain conditions are met. Now, I'll quickly, if you take a look at that now, then when you find this, just going to go into using statistical table, where that is going to be 1 minus p norm of 1, and you're going to have that. Now, let me tell you this. If you are working with proportion, you don't need to add. You don't need to consider continuity correction, because in this question, you've already been told what they gave you. You are seeking the probability of at least 55%. It's already a proportion. You don't need to consider continuity correction. But you can only consider continuity correction if you are working with a whole number, a discrete value. I'm going to show you now. In this example, take a look at this. Suppose y as a binomial with n equal to that, p equal to that. Find the exact probability of y less or equal to 8. 8. If you look at 8. Okay, and y equal to 8. If you use the binomial formula or the binomial table, this is the result. These results are very actual because you are using the binomial, right? So what if in a situation where we realize that that's going to be complex, we can go by way of normal approximation. Take a look at that. Y less or equal to 8, what do you think I've done? I've added 0.5. Continuity correction. Okay? Before I go ahead, computing my Z. Okay? And don't forget, if you take a look at this guy, give me 1 second. Let me go back for less than. So for less than, okay? If you take a look at this, there's a difference between this and this when it comes to discrete. But there's no difference between the two when it comes to continuous. Don't forget, we're dealing with binomial. That's a discrete random variable. They're actually going to have different continuity correlation. That is why this guy has, you are adding 0.5 here, you are subtracting. They are not the same. Okay, now, and that was why you actually have, this guy. If I want to find the probability of y equal to 8, exact value, if you go to continuity correction, for exact value, you're going to subtract and add. Okay, you're going to subtract and add. Do you see this guy? That is for the exact value, y equal to 8. Oh, go ahead. Oh, you mean what is the essence of continuity correction, right? That's a very good question. You know, we are using normal to approximate binomial. Any approximation means we are losing information because you are approximating. So the idea of continuity correction is just to minimize, to reduce information loss due to approximation. If you don't do that, you're right, there's going to be a lot of errors. So which means your approximate value will be far from the actual value. That's a good question. Okay, now so this is using, now if you look at what I got here, is 0.1170 when I calculate y equal to 8 using normal approximation. We got the 0.117. But what if by the time we use the actual probability value, the probability distribution, okay, y equal to 8 using binomial, give you 0.120. That is the actual value. But using the normal approximation, that we got 0.117, they are very close. The approximation is nice. Take a look at that. Okay. Now, and that was why I said, again, we see that this approximate value is very close to the actual value. If I can use normal to approximate that, then why do I need to become worried using binomial? That is complicated when the sample size is large. Another example. A candidate believes that at least 50% of voters support him. To test his claim, n equal to 100 voters are randomly selected. Among them, 45 support the candidate. If the true population of voters supporting candidate denoted by P is indeed 50%, what is the probability that 45 or less voter in 100 randomly selected voters supporting? Okay, if you want to use the binomial, right? If you want to use the binomial, this is how you're going to go, right? You remember in your lower statistics, 100 combination. You're going to go from T to 45, right? T equal to 0, you plug in. T equal to 1, T. You can use it, but look at 100 combination. T, that's so high. That's so high. The computation here is tedious. It's complicated. So the actual value you're going to get using that is going to be this guy. Okay, 18.4%. But if you want to go by normal approximation to binomial, it's just going to be super easy. Expected value of y is p. So expected value of p cap is going to be that. The variance is that. I'll just come to compute my z. It's going to be so easy, right? When I compute my z, the final result that I got for normal approximation is 0.159. Is 0.159. But for the actual, that is 0.184. Very close. You see that? But it is not in our situation that we approximate binomial with normal. Then what are the conditions under which this is the condition? We got a rule of thumb. Okay, the rule of thumb is this. When the sample size is greater than 9, multiply by the ratio of the maximum of p and 1 minus p divided by the minimum of p and 1 minus p. What do I mean? If p equal to 0.3, okay, how many sample size at least we need to have before I can approximate? I can do normal approximation to binomial. You know, if p is 0.3, 1 minus p is 0.7, right? What is the maximum between, if you take a look at this formula, between 0.3 and 0.7 is 0.7. What is the minimum? It's going to be 0.3. By the time you compute this, it means for that, the sample size has to be greater than 21 for this situation, for p equal to 0.3. So if you really want to know, then you need to be able to know what is your p. If you know your p, then you will know the minimum sample size needed. Does that make sense? Oh my God, this is the end of this statistical party. Is there any question? I want to listen to questions now. I want to listen to question now. If there's any question, if you need clarification, is there anyone? Is there anyone? Now, please take notes. Standardization is not about changing the shape of the distribution. Does that make sense? So, if you want to change the shape of the distribution, then if central limit theorem applies, we can do that. But the standardization of a particular probability distribution does not change the skewness. If it is skewed, it doesn't change that. Then why are you standardizing? We standardize to be able to scale the feature, to restrict the mean and variance of that to a particular value that will enable us to use a standard normal table, and that will prevent us from having, you know, infinite numbers of statistical tables. You know, I love statistics because it's very, very, to me, I define statistics as mathematics that makes sense. That is statistics for me. Mathematics that makes sense, or mathematics that has, let me just say, you know, the mathematics that has something that has to do with life, like you can see it. That is statistics. You know, I want a situation whereby you're always going to investigate. I've said some things today that you can also investigate. Start from a probability distribution that is skewed. It could be gamma, exponential, yeah? It could be whatever. Tries to standardize. Plot the distribution of the standardized. It will never follow normal. Even though you have succeeded in bringing the mean of the standard variable to 0, the variance to 1, but it does not change the statistical architecture of the original distribution, you know, in terms of changing the skewness. But what could change the skewness is what? when there's a sufficient large sample and the central limit theorem applies. This way I'm going to stop. Make sure you stay safe and have a lovely weekend. Bye for now, everyone.